Thank you, Daniel and colleagues, for this invitation to Topo-Europe. This is a talk about continental growth in North America. It's made possible largely because North America has been so well instrumented seismologically in the first place over the last decade. But as motivation for Europe, I might say these processes that I'm going to talk about here, crustal growth in the Mesozoic, happened in Europe like that in the Paleozoic. And maybe one day we will be able to reconstruct what happened in Europe with the methods presented here. The starting point is about 200 million years ago, as you can see here in Pangaea, which started to break up around this time along this joint here. And around 150 million years, you can see that the North Atlantic had started opening. From then on, North America would move away from former Pangaea, from Africa, and in this direction. And when such reconstructions are made, what is a general feature is usually that a trench is drawn like that. It's an eastward dipping trench along the west coast of this former supercontinent and also the Americas. And the idea is that as North America moved away, it was under compression here at this trench, and that's how these mountains were built, the North American Cordillera. And this is a model a simple model, and this is a model I'm going to question here, because I think it wasn't quite like that. Looking at this a bit more quantitatively, so North America moved westward in an absolute sense, and these are lines of 10 million years. So 100 million years ago it was here in absolute terms, and every 10 million years it moved westward. This is reconstructed in a hotspot reference frame, so it's absolute movement. We're quite confident that the continent moved west in an absolute sense. And this is solidly constrained because we have the seafloor opening in the Atlantic that left a complete magnetization record on the seafloor. And so the question is, was the trench into which the Pacific domain subducted, was that always along these lines, meaning along the coast? And the standard model asserts that it does. So this is the wildly held opinion. And I'm going to show three time slices here where you can see this more. So 140 million years ago, the situation is supposed to have been like that. North America was still far in the east. This is Yellowstone. So today this would be under the continent. And because this is a reconstruction in a hotspot reference frame, this point will stay fixed. And so 140 million years ago, they're supposed to have been in this Proto-Pacific basin, a huge plate, the Farallon plate. And that is inferred from observations here. This is the young Pacific plate. And as it is being built, we get magnetized stripes on the seafloor here. And from these stripes, we know that there was a spreading ridge, and there was another plate here. Now, this trench is not explicitly constrained to be here. In fact, it's not constrained at all where it is. And the early authors pointed that out clearly. It could have been here or here. But it seemed, because the mountains were along the coast, that this trench was also to be put along this coast. So if I move forward now to 80 million years, you'll see Yellowstone stays fixed, and North America moves in. There's still a lot of Farallon plate or fragments of it, and as we move to present day, North America has overridden this point, and there's only a tiny little bit left, the Juan de Fuca plate, which is Farallon plate. So I can go back once. You can see this, this huge plate is now supposed to be under North America. And if it more or less sank vertically, then the geometry in the mantle that we should have should look something like this. So this is North America. We have this Pacific basin subducting in here, so this supposed Farallon plate. And as soon as the plate comes in here, it should more or less go down vertically. So if we have a continent that keeps overriding this, then in the end we should have some sheet-like thing that slopes eastward under the continent. That's the prediction. And the strange thing is that the mantle under North America doesn't look like that at all. In fact, it looks very lumpy. So slab, subducted lithosphere, as seismic tomography sees it, is concentrated in a few places. And I'm talking of lower mantle structure here, and it's concentrated in these linear arrangements here. I've drawn them at 1,500 kilometers depth, but if I had drawn them at 1,000 or 2,000, it would look almost the same. So we have slab here, we have some further east. This is the present continent, the pink, the purple. And here I have drawn some reconstructions. They differ a bit, but if you go back far enough in time, you can see that the continent is located east of all this. And so the strange thing is that if there were a trench along this line that moved in this direction, we would expect slab everywhere here, whereas in effect we have it only here, meaning too far in the west, and there's a gap in here. And the other thing that you could note is actually this continental outline does not have the same shape as this slab, which you might expect if you always had subduction under a continental margin. So this is strange. And there's another strange thing that doesn't quite seem to fit with this simple story, and that is that large parts of the west of North America are very young. And so they are accreted terrains, and they accreted in the last 200 million years, in fact from 200 to 50. And they are a few hundreds of millions of years old, so certainly not Cratonic age. And most of them are of oceanic character. That means they are essentially island arcs, accretionary complexes, ophiolites. So the question is, where did all these things come from if they don't look like a continental arc, meaning if they don't look as if there had been subduction here? And so this is something that is not addressed by the current standard tectonic model that we just saw. So the contribution of seismic tomography now is what I'm going to talk about in some detail, because that is my own core area of expertise. The tomographic model I'm going to discuss, I made in 2011. It's a P-wave model of the whole mantle, although in practice we can look only about 2,000 kilometers, using stations that were deployed in North America at that time. And this is US array, which wasn't fully deployed by then. It finished this year, so by now everything has been covered. However, all the North American recordings that were available at that time were used for this. So I would argue that although this study should be redone, and some colleagues have done a more complete rendering, which gives consistent results, that the conclusion would not change because we are looking at lower mantle structure and all of this is covered. And these are the earthquakes that were used for this. This is my only technical slide. The point is we were using cutting-edge methods. Finite frequency tomography, or that's a flavor of waveform tomography that uses the full wave sensitivity of a wavelet like this, as opposed to simpler methods like onset picking in conjunction with ray theory. It did make a difference in this case because you can see somewhat deeper. You cannot see twice as deep, but at the edge of the resolvable domain, so in the deepest part and the edges out into the ocean, you do get clearly better resolution. And as you will see, most of this discussion is about such parts. I'm rendering the tomographic models from now on in 3D, which is different from what they are usually rendered. A typical rendition would be this. So this is a 2D section. In this case, it's 600 kilometers deep under Western North America. So usually you would see seismically fast structure, which at this depth means subducted lithosphere slabs, what we're interested in, and slow structure. Now, since I'm not interested in slow structure, I'm not going to render any of this slow. And so what I'm doing is I'm contouring in 3D all the blue things, the seismically fast, but I'm showing it at all depths. So not just at 600 kilometers, but also at every depth below it. And that means depth, color now codes for depth. So you can, for example, recognize this anomaly, which is this, but you also see everything that is underneath it. So in this rendering, for example, you can see Yellowstone is here, but Yellowstone is underlain by quite a lot of subducted material at deeper depths. And the color changes every 200 kilometers. All renderings will be like this from now on. So now we can return to this strange lumpy distribution of slab. this parallels the east coast, so it's under the current east coast of North America, and it trends from Newfoundland into Yukon. And it has been known for a long time. It's in fact one of the largest slabs anywhere in the mantle. The so-called Farallon Slab was first described by Stephen Grant in the early 1990s, and it's present. Essentially, it fills the lower mantle from 1,000 to 2,000 kilometers depth, roughly. And then there's this more westerly structure that has been described only more recently by work that I've done with collaborators in 2008. The surprise there was that these deep things, while they had shown up diffusely in earlier tomographies, including, for example, by Wim's group, the connection had not been visible. So this is what US arrayed. We know what goes in here is the Juan de Fuca plate, so we know this is a Farallon plate. This is Farallon plate, and we now clearly see that there's a connection down to 2,000 kilometers depth. So this now we know is Farallon plate. Looking at the whole picture here, so here you again see this huge slab at all depths, and you see there are white spots. So this is what I mentioned before. There is not slab everywhere, and this is the base of what I just showed. And now I'll show this same scene in a 3D view as if we were hovering over Greenland and looking down obliquely like a satellite. And then it looks like this. So here would be Greenland, and we're looking down. And here you see the very wall-like character of this. So it's very steep, it's very concentrated, and it fills essentially 1,000 kilometers, so from 2,000 kilometers depth to about 1,000. The other thing to note here is that at some depth it then rapidly stops, at least here in Canada. And the next picture I'm going to show is exactly the same thing, only that I'm going to add structure in the transition zone, so in the upper mantle. And then it looks like this, and you see it changes quite a bit. So the transition zone is smeared out westward. It's more like a pancake. Oops. So this is going back, only the lower mantle and the transition zone. So you can see the character of the slab changes quite a lot. It's as if it's now being dragged out towards the west, meaning towards younger times. Okay, more things to note about this. So this here is this Farallon slab, as we said. So it's now recognized to be a Farallon slab. And it is very massive. In fact, the further you go down, the more massive it gets. So it contains a lot of lithosphere. In fact, enough to account for all the magnetized seafloor that's recorded by the Pacific. And then that begs the question, so if this is Farallon slab, and the currently subducting Farallon remnant does not subduct into this, which was previously assumed before we imaged it, so then the question is what is this? I mean, this has always been seen as Farallon, but that's the question then. And the other interesting feature that has not been remarked on like that is these walls are quite wide. So they are too wide to be just a single sheet of lithosphere. They are about 400 to 600 kilometers wide, so about 4 or 6 times too wide. And they're extremely steep, so they are walls. And the final thing that you might note for later is this peculiar promontory that goes out so far east, and that shallows as you go westward, as if subduction had stopped much earlier here than here. So how could such a wall then be built? That's the question, if it's not a single lithosphere. And this is a question that geodynamic modelers have addressed in the last 10 years or so, as it became possible to model the sinking of thin viscous sheets more realistically, both analog and numerically. And so it turns out that viscous sheets fold. This is a syrup experiment, and it has as a backstop a glass plate, but this is meant to simulate the viscosity jump from the upper to the lower mantle. So if you have such a backstop, certain conditions on the viscosity of this and the so-called ambient mantle, you will get a broadened slab like that. The trench is stationary here, in the end, you will get a slab wall that is roughly 5 times wider than what was coming in here. So this is a way to build such a wall, and this is also shown by numerical experiments in certain corners of the parameter space. So the question is then, so this suggests a different model for how these slabs under North America would have been built, and that is they were built while North America was still far in the east. If these slabs are old enough to be from then, and the fact that there's so much lithosphere in this because this is such a folded thing suggests that this might be plausible. So these might be older than we thought. And these might have been built by trenches that were intra-oceanic rather than along the coast here. And because they were intra-oceanic, they could sit stationary in the ocean, and they didn't have to migrate as a trench along this coast would have migrated, as we know the continent migrated. So the prediction that needs to be tested here then is these were long-lived stationary trenches that sat here in the Jurassic and subducted in this direction because there was this open ocean between Pangaea and these trenches, and they were made from the plate, the tectonic plate that subducted into here as North America would come in and override these trenches and any arcs and other oceanic material accumulated above them. So as a cartoon, this would look like this in the Jurassic. We have a trench sitting here in the ocean, and it can sit stationary. In fact, it's probably stabilized by this slab. Once this is in the lower mantle, it's quite inert, and it won't move back and forth. It'll just sink. So it'll sink vertically, and as this ocean closes here and North America moves in, this slab gets deposited. This also makes a prediction of what happens next. So this one we just saw, this is while this trench and arc are active, but at some point this ocean has closed, and this is shown here. And then this subduction must stop, meaning it stops building this slab wall. We get this sharp upward truncation, which we did see under Canada. I pointed that out. And it also means this arc now stops. So there should be a date on this. And what happens next, though, because as we know, North America kept moving, now at the latest now, this plate that is here, which is the Farallon plate or anything that was sitting south of it, is now forced to subduct. And because this margin is migrating, it will now produce a slab that is not so vertical as this one, but it gets drawn out in the transition zone. And this was this blue pancaking stuff that I pointed out. So in fact, this looks like it could be a valid explanation. And the nice thing about it, it would also explain why all of this material, so all of Alaska, most of British Columbia, a lot of the US and most of Mexico, is made up of island arcs, essentially. That's because they were sitting above these long-lived Mesozoic subduction zones, and when North America came along, it collided with these island arcs and accreted them to its margin. How to test this then? Well, so we have the prediction from these positions we have from the stripes on the Atlantic, so from plate reconstructions. So we have a prediction of when this margin was where, and from the tomography, we have the prediction where these trenches and arcs and terrains were sitting. And so, for example, we have the prediction that at 140 million years, North America should have hit here, should have hit the first arc here. So we would be looking for an arc collision and accretion in that place and around that time. This idea is not totally new. In fact, from the complexities of the arc terrains in the Cordillera, it had been suggested that this Andean-style simple eastward subduction model is not adequate. And this is an example. So a few geologists have proposed Archipelago Solutions. This one is from a paper by Moores, and he just took the situation in Japan today and the Philippines, and he mirror imaged it and put it in front of North America to show symbolically this is that something that must have happened in some form there, but we don't have very precise constraints on it. So the idea has been around. It has not gained wide traction, though, in the geological community. The standard model, which I also showed in the introduction, is something like this, and this now is a quantitative reconstruction. So we have here the spreading of the Pacific, and so the prediction here is that all of this would have been Farallon plate, and the trench here, which leaves unexplained why all of these here accreted during the Cretaceous and weren't already there at this time. So this model that's from magnetics just doesn't account for all this crust. So this is quantifiable, and it's because we can infer from this scenario, we can infer a slab sinking rate. Slabs are not datable per se, but if we match it to these accretions, then we can get a prediction for when they should have accreted. So we can say the margin, the plate tectonic reconstructions can say at a certain time the margin was here. So let's say that was time t. And we can see today that the slab that must have hosted this arc is now deep. And so the sinking rate, because this here stopped building, was t at time t. And so dividing these two numbers, we get a sinking rate for such a wall of about 10 millimeters per year. And so you can do this at different places along this whole wall assemblage, and this number is always 10 plus minus 2. So that seems the rate at which these walls sink. And this is also the predicted time, so this time t of a terrain collision. That's a geological observable. So that now needs to be checked whether there was actually terrain collisions in the times and places predicted by this scenario. So putting this all into place, we can now say at 140 million years, we can plot all the slab that should have been present at that time. That means it's all slab that's deeper than 1,400 kilometers for the sinking rate. That looks like this red. And so we can say, okay, here the trenches must have sat. And because there was still space between North America and these trenches, and this had to subduct this ocean, which we call Mescalera Ocean and Angayucham Ocean after ophiolites. This had to subduct, so we know it had to subduct westward. It had to be westward subduction. And now it's a question of matching all the accreted terrains and two accreted super terrains to these trenches. And so there were actually some super terrains already accreted earlier. That must be a story that lies deeper in the mantle. But what must have accreted at this time was a microcontinent called Wrangellia, and some other super terrains here. And this here is going to be future Alaska. So if you watch in the next slides, Alaska wasn't there at that time, and this will become Alaska. Now maybe you can focus first. I'm going forward in time now, so I'm going to show here's 140, then comes 110, then 75, and then 50. And maybe first you can watch just this slide and see what happens. So this is 140, and then at 110, North America is moving east, and you see it's starting to ride into this terrain assemblage and colliding with a wider and wider swath, which corresponds to the Rocky Mountain orogeny that spreads along the margins. So a wider and wider swath of the margin is affected, which was actually observed around that time. So now moving forward to 75. You can see we're well into the assemblage now, so most of it is overridden. In fact, now we get to a point where the Farallon plate finally touches the North American margin, and so now we're starting to see eastward subduction, which is actually recorded in the Franciscan Formation under California, so we have AGU every year. And you can also see that all this red stuff is mostly overridden now, and it is moving into the place of Alaska. And if I move forward to 50 million years, you'll see that even this last little stuff out here will be overridden, and that's the end of the sequence. So we predict that from the slab geometry at about 50 million years, this terrain accretion sequence should have been over, and in fact, that's also where it was over roughly. And now we get an Andean-style margin because now the Farallon plate is touching the margin and has to go under here. So I'll just go back in time so you can see this once more. So opening this archipelago again, and here it gets overridden. And if we, and I'll just go, oops, sorry, just go back again. Now, looking at the tomography, so all I did here is that I always plotted at this time where North America moves in, I plotted all the slab that should have been present. So you can see this promontory first gets overridden, and so it's predicted that the orogeny should have started here. It did. It started in the Pacific Northwest. It's an episode called the Nevadan orogeny. And then, as it overrides more and more this archipelago, there should have been more and more mountain building, which is observed. It's the Rockies orogeny. And as we move further, now this slab, the big one here, starts to have been overridden, and now it gets really messy. There come things like the Laramide orogeny as it overrides the remainder of this archipelago. And here, it's then over at around 55 million years. And we have an Andean margin. So the summary then, in Jura-Cretaceous times, this standard model does not seem to work. So newer geophysical evidence does not support this Andean-style subduction with the empty Pacific as we have it today. And it does support these non-mainstream models that an archipelago must have been overridden and formed the North American Cordillera and did the mountain building and did it in episodic ways as it was observed. But the new thing is that with the geophysical evidence of the slabs in the lower mantle, surprisingly, so deep down, we can quantify this. So we can say where, in absolute terms, these terrains must have sat and when they should have been accreted, and this is testable against geological observations. And at the same time, we learn something about the rheology of the mantle, that is that these deep slab walls, they seem to be sinking at 10 millimeters per year. And all what we found here is consistent with that they simply sink vertically in place. This is important because previous explanations of this very lumpy slab geometry always had to explain why they are so lumpy. And if you have a continuously migrating margin, you can only do that by having very differential or non-homogeneous sinking, faster in some places, slower in others, and very non-vertical, so you're moving stuff. And with this model, this is not required. So it makes mantle sinking simpler, the rheology, and it explains why there's so much accreted material at the North American margin. And that's it. Thanks.
All right, thanks very much. I don't know what we should do. If we need to save time, do we keep the questions or do we jump to the next one? We should have questions. So questions, he said we should have some. Sean?
In your model of west-directed subduction, is it really necessary to have no subduction at all? Hello? Oh. You have, in fact, in your sketches, more of a strike-slip system that runs up the, say, the Jurassic-Cretaceous west coast of North America. But could that not also be double subduction, subducting to the east under North America, while at the same time having the arc system out to the west? And in particular, I'm concerned about things like why would we have a Cretaceous seaway if we have no subduction in that direction any longer?
Well, I think at that time, I think of so for the first half of your question, there is no slab under the Atlantic at appropriate depths. So at least on a large scale, there was no subduction in this direction if we have no slab here. Unless, yeah?
But do you really have enough resolution under the Atlantic to say there's no slab there?
Yes, and at those depths, yes.
You're sure?
Yes. And your second question, I think of the Cretaceous seaway as something that happens. So we have a passive margin for a long time. In the Cretaceous, the sea level is quite high, so that margin is flooded. It's underwater. And then what happens next is the terrain accretions start in the Jurassic and early Cretaceous along the margin, and so that margin gets uplifted. And so now we have the western welt, you know, of an uplifted passive margin that's not passive anymore, whereas the middle is still underwater because of the high sea level.
It's not really a passive margin, though.
No, then it's not a passive margin anymore. Well, no.
Even eaten by Jurassic, I mean, it wasn't a passive margin.
Yes. By Jurassic, it's not a passive margin anymore, and that's because there was at least one previous. So this is another super terrain, Canelia, Stichinia, and the Cache Creek Ocean, and that happened in Jurassic. So that must be one story deeper in the mantle, and there is slab, but our resolution is not so great at the moment. But before that, there was a passive margin.
All right, there was a question right there.
Hi, I'm Peter DeSalle from the University of Arizona, and I've worked in the thrust belts in the Farallon Basin and the magmatic arc in western United States for about 30 years. And the reason that Eldridge Moore's model has not been widely accepted, there are many reasons, but I would say that in simplest terms, with respect to what you're presenting here, there's a Farallon Basin that laps on to North American craton. Its continental scale runs entirely up and down the western half of North America for approximately 150 million years. There's a well-studied fold thrust belt outboard of that. North of the Canadian border, that thrust belt, broadly construed as the Cordilleran orogenic belt, contains a number of accreted terrains, most of which have some island arc affinities. South of the border, however, there are no well-documented oceanic affinity terrains, particularly in the basin and range after Paleozoic time. The thrust belts are, the backstop on the thrust belt is a gigantic magmatic arc, which was active beginning about 220 million years ago. The Sierra Nevada continues on down into the peninsular ranges. That's built in North American native crust. So there's a continuous subduction margin that goes from about 155 million years ago inboard through a magmatic arc, which is in North American basement, which is flanked by a Farallon Basin that laps onto North American craton. It's very difficult to explain that without eastward subduction starting by about 155 million years ago. So I think that the tomography is extremely interesting, particularly with respect to Mescalera. But I agree with Sean. I think that Mescalera needs to be subducting eastward as well as westward.
We acknowledge the necessity for this native Jurassic arc. So yes, that's an observation, and so yes, there must have been subduction that lapped onto the margin. However, so that was accreted by about. So that, because that is then this Canelia, Stichinia, and Cache Creek complex that it becomes in Canada, and it onlap, and this is in purple here. So yes, before this story that is shown here, there was another episode that created this, and there must have been some eastward subduction, but here, unless Wrangellia and these super terrains were fused early, for which there's no solid evidence as far as I understand, this model is possible.
Okay, there's plenty more questions, but I think it's time to move on.